As computing becomes integral to the fabric of human society, so must computational thinking as an essential skill to empower scientists and engineers to extend their abilities to further advance technologies. However, driven by the slowdown of Moore's law and the rise of big data applications, a new era of computing emerges, spawning a series of new challenges that computer scientists must face. While new computing models such as quantum computing and DNA computing are under continued development, some researchers believe that the conventional von Neumann architecture also can be further developed for a great future.
In our study, we proposed a new thinking paradigm, HCDA. We combine 4 points together. That's historical thinking, computational thinking, data-centric thinking, and architectural thinking. We combine the 4 things together in order to exploit the potential of von Neumann architecture.
Historical thinking explores solutions and methodologies from past results, lessons, and experiences. Computational thinking focuses on making the machine faster, for example, via parallel computing, and more functional, for example, via AI. Data-centric thinking from a behaviorism perspective implies solving problems via data. From a mechanism perspective, data-centric thinking implies memory-centric design, making the impact of data access delay as small as possible. Architectural thinking refers to utilizing existing transistors to build optimized computer systems through hardware and firmware designs.
Only computational thinking is not enough for our current life. In our education and research, we should keep the 4 pointers in our mind. We should not partially use only one of them or 2 of them. And in our real design and the implementation, the 4 pointers should be connected together.
Historical thinking provides inspiration and foundation for the other 3 thinking patterns. Computational thinking and data-centric thinking can be implemented physically through architectural thinking. Due to the combined impact of filtering and feedbacking, CPU performance and memory performance are entangled and mutually influenced by one another. Therefore, they need to be matched and considered in parallel. High-speed computation requires rapid data movement, and data movement is a critical factor for next-generation architectural design, either from computational thinking or from data-centric thinking perspective.
The computation and the data and architecture and the history are objectively and inherently symmetrical with each other, so they should attach to equal importance.
Enriching computer scientists with HCDA will boost innovation and provide corresponding actions that enhance the impact of technology on our rapidly evolving society. The 4 patterns of thinking and their corresponding actions constitute an effective paradigm that can facilitate the advance of computer technologies in the new age of computing. Learn more in HCDA, From Computational Thinking to a Generalized Thinking Paradigm, a contributed article in the May 2021 communications of the ACM.